I want to see how does it handle this, absolute value. The textbook does not. I look at the textbook, it does not use the absolute value. Yeah. But we need to understand why, right? Yeah. The textbook does not explain why. Yeah. But here I use my own understanding to explain. Yeah. Because I check the textbook, natural log here, this place, this place, no absolute value. All right? Yeah. So let me explain a little bit why this place we do not consider absolute value. There is only possibility, that is when x is positive. Only in this case, so we do not consider absolute value. Yeah. So it looks like this is some hidden assumption there. Yeah. Based on what I saw in the textbook. Why? Let's look at this power function here. X to the m. X to the m. But the m, our m here is a real number, right? Our m here is a real number.
Right, and even if it's negative, it would still have to be greater than 0.
If x is negative, what's the meaning of x to the mth power? M is a real number. It's not an integer, not positive integer, not negative integer. M is a real number. So here you consider a negative number, you raise to mth power, but m is a real number.
Say if m were negative, the domain of x would still have to be positive.
Yeah. So this place, so my question, so yeah, for example, so here we can consider negative 1 to the square root of 2. If you have this one, this is a complex number. This is a complex number. So that means for a power function, if you allow x to be a negative number, then you need to consider a complex function. It's not a real function. Okay? Yeah. So then, although people may say it's okay to complex functions, but in the real world applications, if the complex explanation does not make sense, then if we want to restrict ourselves in real functions, then we need this x positive. Okay? If x negative, then power function will give you the complex numbers. Okay? So that is partial reason. All right? Yeah. But for another part, I need to check the history of this Euler-Cauchy equation. Yeah. Because it came from some background. Yeah. So let me double check the physical background of this equation. Yeah. And use that background to understand positive and negative. Okay? Yeah.
Thank you.
All right. Okay, good. Yeah, good question. Yeah. So we need to explore a little more. All right. Let's move to the next topic. Yeah. So we're here. Yeah. We saw a trivial example, but this time we want to study a non-trivial example. Because usually the trivial example does not give us any useful information. Yeah. So if we can find a non-trivial example, then we can find much more useful information. Yeah. Here, we have this non-trivial example. Yeah. To solve this initial value problem, we use the separable structure. Yeah. The integral like this. Yeah, absolute value. Yeah, this time we have to use the absolute value in these two places. Yeah. Then some constant C star. Yeah. because this is an intermediate constant, so we use that C star. Yeah. Because later we want to replace this constant by a different form, so we will use C later. Yeah. All right. Then absolute value on y, that means we should have absolute value for y, and at the same time absolute value for y minus 2. Those two absolute values we can take care of by this plus sign minus sign, right? Yeah, because the relationship plus or minus. Yeah. All right, but next, look at this coefficient part. Could be positive, could be negative, and e to the c star, some constant. Can we use a simpler way to represent this coefficient part? Simpler way to represent the coefficient part. Yeah, right? Yeah. So the simple way is that we can use just the one c, because the c could be positive, could be negative, right? But this c cannot be 0. It's a non-zero constant. Yeah? Because e to the any constant cannot be 0, right? Yeah. E to any c star constant can never be 0. Yeah. So for that reason, if we want to use a simpler way, we replace that, relatively complex form by the simple c. But we want the simple c non-zero constant. Yeah. Could be positive, could be negative. Okay? Yeah. That's the solution. Yeah. All right. But after we get the solution, let's plug in the initial value. Y of 2 equals 1. We want to determine that little c. But when we plug in, then we get contradiction. Yeah. Because if you plug into the y function, x minus 2, you get 0. 0 times c, also 0. But the initial condition tells us y of 2 must be 1, not a 0. So that's a contradiction. If you get a contradiction, that means this initial value problem does not have any solution. Yeah. All right? So here you can see, you find this is a non-trivial example, right? So in this non-trivial example, the initial value problem does not have any solution. The conclusion. Okay? Yeah. But we need to understand why, right? Yeah. So we agree, based on our calculation, it does not have any solution. But we want to know why it doesn't. What caused the problem? Something must be wrong, right? Yeah. If there is no solution, something must be wrong. So we want to see what's wrong here. Yeah. All right. Can you observe anything special here? Yeah. The property, some special property? Yeah. Yeah. If we write so we go back to our original. This is our original equation. But this equation is not in standard form, right? Yeah. Because this is the standard form. Y prime equals some f function. Yeah. So we need to convert it to the standard form. The standard form should be y prime equals 1 over x minus 2 times y. Or y over x minus 2. Yeah. All right? Yeah. But after you write it as a standard form, then y minus 2 is at the denominator. Right? Then your initial value 2, that 2 happens to be the point that makes the denominator of f function 0. Denominator becomes 0. That's the reason. That's the reason this IVP, initial value problem, does not have any solution. Okay? Yeah. So we found the problem. Yeah. Okay? F function cause the problem. Yeah. All right. Yeah. Because it's not in the domain of F function. Yeah. So this function, the domain exclude x equal 2. So x equals 2 is not in the domain of that F function. Then the IVP problem does not have any solution. Okay? Not in the domain. Yeah. All right. But from this example, yeah, so we want to, further get this existence theorem. Yeah. Here in our class, we will not prove it. Yeah. So because this course is not for math major. Yeah. So for math major students, then this important theorem, so we must prove it rigorously. Okay. Yeah. But for engineering students, then I just explained the theorem. Okay. So I will not prove the theorem. Yeah. All right. So let me explain the existence theorem. Given the initial value problem y prime equals f function with two variables, x, y variable. Yeah. The initial condition y of x0 equals y0. Yeah. Then we define a neighborhood of the point. Yeah, because the initial condition occurs at this point. So that means this point is important. In order to make this IVP problem satisfy the given initial condition, so we need to study some neighborhood of this point. So what do you mean the neighborhood? Here we define neighborhood in this way, this R. We use this capital R representation, the neighborhood. Yeah. First, around x0, we consider an interval. Yeah. So the distance of x to that x0 could be positive side, negative side, two sides, right? Absolute value. So you consider the distance of x from x0 point from positive side and the negative side, two sides. But that distance must be less than some constant number a. Yeah. Yeah. Positive constant. A must be a positive constant. Okay. Yeah. And for around y0, you also consider positive side, negative side. The distance between y and y0 must be less than another constant, positive constant b. Yeah. That's the neighborhood. Okay? Yeah. That's the neighborhood. So if I draw a graph, yeah, because you want to have some visual understanding, right? Yeah. Visual understanding. So the x0, y0 point, yeah, for our corresponding to our initial value. Now we define our neighborhood I for x. We consider some small interval, yeah, yeah, a, okay, yeah. All right. For y, b, okay, yeah, the width of this belt, b, okay, b, yeah, and this rectangle is the r, okay, yeah. And x0, y0 is at the center of that rectangle. Yeah. The R is a rectangle, yeah, and we call it a neighborhood. Okay. All right. Yeah. So that's the condition. Yeah. Then, yeah, that's the setting. Okay, all right. Then, the condition. The f function f of x, y has the following properties. In order to have a solution, yeah, existence. So our goal, we need to make sure there is a solution for this IVP problem. In order to have a solution, yeah, so this f function must satisfy the following conditions, yeah, or properties. Yeah. It is continuous at all points in R. This function must be continuous everywhere in that neighborhood R. Okay? Yeah. In our previous example, this condition is violated, right? Yeah, because at the center, at x0, y0, it's not continuous. Okay? It's not continuous. Yeah. It's infinity, right? It's infinity, so it's not continuous. Yeah. All right, to the first condition. The second condition, this f function is bounded in R. Bounded. Yeah. Bounded function. Yeah. So what do we mean bounded? Here, let me give you the bounded function, the definition. Yeah. There exists a number capital K, yeah, some constant K, capital K, such that this f function, absolute value of f of x comma y, less than or equal to capital K for all points, x, y points in R. That's the meaning of bounded function. Yeah. But so here there is a certain positive constant K, capital K. Yeah. All right. So under these two conditions, number one, number two, then the conclusion. The conclusion says this initial value problem has at least one solution f of y of x in a smaller subinterval, right? Yeah, smaller, yeah. Smaller of this subinterval, yeah. Yeah. Because sometimes we need to make it smaller, all right? Shrink a little bit, okay? Yeah. But still, you have a subinterval, all right? Yeah. And specifically, how smaller, right? People want to ask how smaller it is. Yeah. Then, the specifically tells you how smaller. This subinterval is absolute value of x minus x0 less than alpha, another constant, new constant, alpha. Yeah. This alpha is smaller than a, than the previous, that a constant. And alpha could be given minimum of a and b over capital K. So this bound, capital K, this upper bound constant should be used. Yeah, yeah, yeah. So you may ask why this alpha, right? Yeah, this alpha, because you need to look at the proof. In the proof, in order to make the whole proof work, we need this smaller alpha. All right? Yeah. In the proof, yeah. The technique, you can say this constant alpha relies on the technique used in that proof. Okay? Yeah. If you change to a different technique, probably you can improve that alpha. Okay? Yeah. But this alpha relies on the specific technique used in the proof. Yeah. Yeah. But here we do not go that far. Okay? So we will not dig into the proof. Yeah. 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 If some students really want to see the proof, yeah, you can go to the appendix of our textbook. Yeah. Yeah, so that is the existence theorem. Yeah, existence theorem. All right? Yeah. But for first order, okay, still not our second order yet. Yeah. But we need to, get a concept, get a, arrangement based on the first order ODE. Second order similar, yeah, we just change a little bit. Yeah. All right. Existence theorem. Yeah. All right. Checking previous. Yeah, definitely. The f function is this one. You can see the first condition is violated. Second condition also violated. The first condition because it's not continuous at x equals 2, that point. The denominator is 0. So it's not continuous at that point. Yeah. The second condition, it's not bounded. Yeah, because infinity. Yeah. So in that center point of the neighborhood, so the x value goes to infinity. Infinity, so no bound you can use, to put the f function under that bound. Yeah. So there is no bound. Yeah. So both conditions are violated. Yeah. So that's the reason, you cannot. Okay? Yeah. All right. Now, let's move to the next topic, is the uniqueness. Yeah. Yeah. Because when you have the existence theorem, yeah, it guarantees there is at least one solution. Right? But the question is it possible you have more than one? Right? Yeah. So we need to study under what condition you only have unique solution. Yeah. Not more than one. Unique solution. Yeah. So that's also important. Yeah. All right. So let's this time I just give you the uniqueness theorem directly. Yeah. But when I give you this theorem, you can see a lot of setting. The setting is the same as the existence theorem, the setting. Yeah. But the condition part is different. Yeah. Here, let's only look at the condition part. Yeah. Yeah. The condition part, f function is continuous at all points in R. Yeah, this condition is the same as our existence theorem. Yeah. So no change on condition 1. Yeah. But condition 2, it's different. Condition 2, we need to look at the partial derivative of f function, partial f over partial y. And we require that its partial derivative is continuous at all points in R. That's a new condition. Yeah. Partial f over partial y. Yeah. Condition number 2. Number 3, this time, for the boundedness, we want both functions, f and partial f over partial y, are bounded in R. Yeah. F bounded in R, that's our old condition, right? The existence condition. Yeah. But we add a new condition, partial f over partial y must also be bounded in R. Yeah. Yeah. Then our conclusion. Yeah. After this conclusion, yeah, the bound here we just use two different constant. Yeah, capital K, capital M, two different constant. Yeah. Conclusion is this initial value problem has at the most one. Okay? Yeah. Existence, that one, at least one. This here, at the most one solution. Right? Yeah. But because these three conditions covers that existence, the condition, two conditions for the existence theorem, right? Yeah. Yeah. Covers that. That means with these three conditions, we already have the existence part, right? So we have both existence and uniqueness. Yeah. We have both greater or equal to 1 and less than or equal to 1. All right? the existence tells us the number of solutions greater or equal to 1. This uniqueness, so here, existence, okay, tells us. And uniqueness tells us less than or equal to 1. Then we combine these two, so then initial value problem has exactly one solution. Yeah, because we have both existence, uniqueness, conclusions. Yeah. So we put them together. Yeah. So our conclusion is, so this given initial value problem has exactly one solution, y of x. Yeah. Yeah. That's for the first order ODE result. Yeah. Yeah. It belongs to chapter 1. Yeah. So I put it here because we need to continue this topic and extend it to second order ODE. Yeah. So we can save some, discussion, redundancy. Yeah. All right. So let's move to the, so the example. So here, so study this example. Yeah. So before we go to the second order, let's look at this example. Pretty simple, but some interesting things I want to talk about here. Yeah. All right. First, because if you look at the equation, it's so simple, we can find a solution. We can solve it, right? Yeah. Yeah. So usually, so if I go back to the previous slide, here, previous slide, usually when we apply this existence as the uniqueness theorem for certain f function, most of the time we may not be able to find an analytic solution. Formula, explicit formula. Most of the time we cannot. Only when the f function relatively simpler, then we can find analytic or specific formula for the solution. Yeah. So although we can show the solution exists and is unique, but its formula cannot be found. Yeah. The reason is too hard. The formula, the specific formula may not be available. Okay, may not be available. Yeah. But some of you may ask this question: if the specific solution formula is not available, how do you know the solution exists and is unique? Right? Because you cannot find the specific formula. Yeah. The answer is simple. Yeah. The solution exists. Although the formula cannot be found, but we can use the numerical values to approximate solution, right? Numerical values I mentioned before. People can use the numerical values to approximate the function. All right? Yeah. And in real-world applications, most of the functions may not have formulas, right? Most of the functions may not have the formulas. Yeah. But we can use the numerical values to approximate those functions. Yeah. So that's the real-world situation. Okay? Yeah. Because usually you are not that lucky to have explicit formulas. Yeah. Usually you have set of data. Yeah. Here, let me explain. Yeah. Because this understanding is important when you work on the real world applications. Yeah. All right. In the real world situation, usually you are given a set of data. So this function contains the points like that. Okay? A set of points. Yeah. To the X array and a Y array, things like X array. So you have a 1D array containing the X coordinate, another 1D array containing the Y coordinate, just a sequence of points. But you do not have the function formula. No, in the real world, you only have these points, data points, and there is no function. Okay, so that's the most of the time you have this situation. Okay, yeah. So then people use some nice function to approximate. Yeah. Because you don't have the formula, but you can use some nice function to approximate this function. Yeah. All right? Yeah. Yeah. So with that understanding, so that means the solution here, you can get a sequence of data points to represent a function. Because you do not have the function formula, you may not be able to find the explicit formula for the solution. But what do you have like that? A sequence of data points. Okay? Through the numerical computation. That's possible. Yeah. That's, most of the case, you have that. Okay? Yeah. All right. So then because this kind of understanding is important. Yeah. Yeah. Otherwise, you may understand this way. If there is no formula, that means there is no solution. It's not that. Okay? No formula, still we can have solution. Yeah. But a numerical solution. All right? Yeah. Numerical solutions. Yeah. All right. But here we are lucky because here equation is so simple, we can find the formula. Yeah, it's a separable ODE. Yeah, yeah. So arctangent. Yeah. So actually, this should be here. I use this A. This is the way computer science use this arctangent. It use the A tan to represent arctangent. But we should use the math way. Yeah. So here. In math, we never use A tangent represent arctangent. Yeah, there are two ways. First, we arctan y. Okay, so the math way. Another use the inverse function. Yeah, another use arctangent. Some people also use the inverse tangent function. Then you put this -1 inverse function y like that. Yeah, yeah. But I prefer this way because no confusion. So it's arctangent. Because if you use this way, I'm afraid some students may get confused with 1 over tangent. Okay, it's different from 1 over tangent. It's the inverse of tangent. Inverse here means arctangent. Okay, so it's not a 1 over. So it's different from 1 over tangent. Yeah. So that's what. But this representation is very easy to, sometimes when you do calculation, you just replace it by 1 over tangent. Then you get the wrong answer. Okay. Yeah. So that's why in your calculation, it's better to use this arctan. Yeah. But this is the CS way. Okay. Yeah. So we should avoid it. Yeah. Although I put it here, yeah, but because then I check the, web everywhere. So then I noticed that that's the, computer science. Computer science in the programming. Okay, when you use the programming language, yeah, in that, so you may need to use this arctangent A tan. Yeah, that's the computer science way. Yeah, not the math way. Yeah. All right. Then, yeah, so we want to go back to the, arctangent. We know that's the inverse of tangent. So we get y equals tangent of x plus c. Yeah. Then to determine that c, yeah, how to determine that c? Yeah, we plug in the initial value. Yeah, tangent of c equals 0. Yeah, yeah, and we know tangent function is a periodic function, right? Periodic function, pi periodic. It's not 2 pi periodic. Sine, cosine are 2 pi periodic. But tangent function and a cotangent function, it's a pi periodic function. Yeah. Pi periodic, we select one period around this 0. Yeah, one period around this 0. Okay. Yeah. Above 0, half pi. Below 0, another half pi. Okay. So the solution y equals tangent, but in this one period. Okay. Yeah. Yeah. Plus minus pi over 2. Yeah. For one period. Yeah. Yeah. Containing this, initial point. Yeah. All right. Yeah. That's the solution, because here we want to use this simple example to help us understand the existence and the uniqueness theorem. Yeah. Now, let us go back to the theorem, existence and uniqueness theorem. Yeah. Define rectangle R with certain constant A and B. Yeah. So here, A and B to be determined. Yeah. Because we have some freedom to choose A and B. Yeah. But in our textbook, these two numbers are given. Yeah. So you do not need to choose what A, what B. So the two numbers given. A equals 5 and B equals 3 in our textbook. Yeah. But here, I want to do something. Yeah. So I want to do a little more than our textbook example. Yeah. What's that? So here, I keep that unknown AB. Yeah. Then let's apply our three conditions in our existence uniqueness theorem. Yeah. It's bound. Yeah. First, f function must be bounded, right? So let's calculate the bound. Yeah. Because y absolute value less than b, so 1 plus y squared less than 1 plus b squared, and we define this number as the capital K constant. Yeah. All right. Then existence. Yeah, because this condition, continuous condition already satisfied. Yeah, because f function is a continuous function. Yeah. Then the bounded condition also satisfied. Yeah. So the existence interval, we know, in this smaller subinterval, remember the subinterval alpha, based on the formula given, should be the minimum of A and B over K. Yeah. B over K. Yeah. But what is B over K? Yeah. Yeah. Here. And the B over K, there is some uncertainty in B over K, right? Yeah. Because K is determined by B. K equals 1 plus B squared. If you have the B value, then you have the K value automatically. Yeah. All right. But here we want to see, for what B, we have freedom to choose B, right? Yeah. For what B, we want this ratio, B over K ratio, as large as possible. Yeah. Because for different B, this ratio, B over K, is different. And we want to choose one particular B such that B over K is the largest. How about that? Okay? Yeah. So here we do a little more than our textbook. All right. So B over K equals B over 1 plus B squared. Yeah. Now we want to look at, is it possible to find the maximum value of this expression, b over 1 plus b squared. It's maximum value. Yeah. All right. Here, let's convert to b over a 1 over. Yeah, because if we divide it by b in both numerator and the denominator, so we get this 1 over b plus 1 over b. Yeah. And this time, the numerator is a constant 1, right? In order to get the maximum of the whole function, that's the same as get a minimum of the denominator, right? Because we know the smaller the denominator, the larger the fraction. Our goal, we want to make the fraction value the maximum. Yeah. And the numerator is constant 1. So that means we should make the denominator b plus 1 over b as small as possible. Yeah, as small as possible. Okay? Yeah. All right. Yeah. So here, how to get that? How to get that b plus 1 over b as small as possible. Here, I want to talk about there is a famous inequality called the mean inequality. Yeah. I don't know if you heard of that or not. Yeah. Mean inequality. Yeah. Simple form. Mean inequality. First, a plus b over 2. This is we call the arithmetic mean. Arithmetic mean. Mean. So what's mean? It's average, right? What's the meaning of mean? Mean, its meaning is average. Yeah. But for this mean, you may have different definitions for this mean. Yeah. Yeah. One definition is arithmetic. Yeah. This a plus b over 2, this is arithmetic mean. Arithmetic mean. Okay? So left hand side. This one, geometric mean. Another mean, geometric mean. Okay? So this mean theorem tells us for positive constant a and b, its arithmetic mean is always greater or equal to its geometric mean. Yeah. So that is the famous mean inequality. Yeah. But this is the simplest form. Yeah. So there are, mean inequality for 3 numbers, 4 numbers, and n numbers. Yeah. Yeah. The general form. Yeah. But in our example here, we only need to use the 2 numbers. Mean inequality is for 2 numbers. Yeah. All right. Yeah. So people also write AM. That means arithmetic mean. Greater or equal to GM, geometric mean. Yeah. Okay. Yeah. All right. Then here, arithmetic mean. Yeah, because B, these 2 numbers, its arithmetic mean is this. Geometric mean, b times 1 over b, after cancellation, it's 1. Okay? That's why you get b plus 1 over b greater or equal to 2. Yeah. And you have this equality could hold where b and 1 over b equals 1. The equality holds. Yeah. So when b equals 1, yeah, this b plus 1 over b is the smallest number. The smallest number is 2. Yeah. So now we go back to the, our ratio. The ratio should be less than or equal to 1 over 2. Yeah. Because your denominator is greater or equal to 2. Yeah. So the smallest denominator is 2. That means the largest fraction value is 1/2. Now, when your denominator is the smallest number 2, your fraction takes the largest number 1/2. Okay? Yeah. So that's the, So if you want to choose your b to make this ratio larger, or to make this alpha larger, so the best B you want to choose is 1, okay? Yeah. But in our textbook example, B is chosen 3. Yeah. If you choose 3, your alpha is not the largest, okay? If you choose 3, your alpha is 0.3, okay? And if you choose 1, the alpha is, if you choose B equals 1, the alpha equals 0.5. 0.5 greater than 0.3. Okay? So you make your existence interval as large as possible. Okay? 0.5. Larger than 0.3. Okay? Yeah. All right. So through this example, although in this example we do not have to do this. Yeah. But here because this property is interesting, yeah. So I use this chance to introduce you this mean inequality. Okay? Because it's very famous. This mean inequality very famous, very powerful. Yeah. So I just introduce here. Yeah. All right. Yeah. Yeah. I mean, so then we have both. Oh yeah, for uniqueness, you also need to check partial derivative. Yeah. Okay. Partial derivative bounded, partial derivative continuous and bounded, right? And the partial derivative is continuous, no problem. Yeah, because this function 2y continuous. Yeah. So no problem. It's bounded, so you know the 2b is the bound. Yeah. So you have the uniqueness. All right, yeah, so we run out of time today. We have a last topic, and we leave next time. Okay, yeah. All right, so let's stop right here. And I will give you our first homework assignment tomorrow, okay, sometime tomorrow. Yeah. So that's, you need to start work on first homework. Yeah. All right, that's it.